So as I was saying, I am really more than glad to welcome Professor Holger Karl, who make us the honor to join our scientific committee. And as part of the committee, he will participate to the meeting we have, the workshop we have with the scientific committee every year. And the next one will be organized next June. And as you probably already know, but I will make it short, Holger is a international renowned expert in networking, working these days, if I'm not wrong, in 5G and beyond, including in particular different tools of artificial intelligence to design these networks. I will let him introduce more details. But again, Holger, very, very welcome. Thank you very much for joining us. And maybe Ludovic, you want to say something?
No, I think you said everything to be said.
Ludovic is just Holger as a member of our committee, just for you to know. Ludovic is a member of the executive committee of LINX, as he's leading in particular, among many other activities, he's leading this seminar. And we have also online François Bacelli, Professor Bacelli. Maybe he's another member of the executive committee. Maybe François, you want to introduce yourself? I mean, to say hi, because everybody knows you, of course.
Indeed.
And
yes, time to unmute my mic. Yes, nice meeting you, Holger, and I look forward to more interactions. Thank you. Same here. Thank you.
And I don't know if we have other members of the committee, because I don't know how to list the people
I
that
didn't
is.
see
Sebastian
Tixey, who is not here today. Usually he participates, but here today he cannot join. And neither Makluf Haji from Systemix.
Okay. So anyhow, Holger, welcome again, and the floor is yours.
Okay, thank you. Thanks a lot. Thanks a lot for the invitation to the scientific committee and also to the seminar here. I'm very happy to join this group. And for today, I understand we have about an hour. Rest assured, I'm not going to talk for a full hour. I know this is tough to sustain over such a video conference. What I would suggest to do, I'll go over the slides, and if you have any questions, please immediately interrupt, ask in between. I'm not sure I'll be able to follow the chat, so I guess it's best if you just speak out. I catch that then. Does that sound like a good procedure? Okay, I don't hear any objections, so I guess that's what we'll do and see how far we get with that. So I hope you can see my slides.
Yes.
I think you should. Excellent. So what I would like to do today is to give you sort of an overview of our research in my group for the last 4-5 years. I try to sort of spin a tale where we started from, what we are currently looking at. I don't plan to go into any technical details. I thought for such an introductory talk, that's probably better to give you an overview rather than one specific individual result there. And again, if I'm boring you, if all of that I'm saying is obvious, particularly the motivation part might be fairly agreed upon, or maybe not, right? Please, again, interrupt me, tell me, I'll be happy to move on to hopefully more interesting stuff. So what I'd like to talk today about is the notion of distributing the execution of a service. And I'll circle to the question what I mean by a service in a minute. But before that, let me give you a little overview of topics that we looked at. So as you might know, I've been at TU Berlin before I moved to Paderborn here in the group of Adam Wallisch. So that explains my history in wireless networking and mobile networks. And this is work that we have also continued here in Paderborn for a long time, actually 15 years or so, 16 years probably by now that I'm here. Golly, time flies. In the last couple of years, mostly driven by so-called collaborative research centers on the Forschungsbereich, German DFG funded, how to put that, large-scale research project, something like 15, 16 research groups here. We started also looking into data centers, networking data centers, but also job execution, job scheduling inside data centers. And then since a few years there, we found sort of a nice bridge between these two somewhat disparate topics. And that bridge turned out to be network softwareization, the idea that you can think of a network as an infrastructure in which you can run software, rather than as something that has predefined, pre-built in, shaped, fixed, firm functionality, which you just have to suffer from. No, it's something where you can run whatever you like inside, quote unquote, whatever you like. Okay. And it is indeed this area of network softwareization that I'd like to focus and concentrate here in the talk. And time permitting, I'll give you, excuse me, time permitting, I'll give you some hint or some taste of the other research areas as well. So with that being said, I'd like to start with what I mean by services. Now, if I look at software being executed in commercial applications, and if I talk to my software engineering colleagues, there's nobody is running a service or an application as a big monolithic executable. Rather, you chop up your executing software into small individual components, each of which can run on its own and specialized to a particular functionality. And then you have these microservices being stitched together into what is then called a microservice chain, or maybe just a microservice. For brevity, both the component as well as the conglomerate as such is called that quite often. So the default example here would be you got your user talking to a web server, your Apache Nginx or something, talking to an application server that has all the application code, and maybe behind that you have a database, right? That's your typical distributed systems, 3-tier web application stuff you teach in a bachelor class. And what could be more natural, right? This is a very neat structure if you need to think about what happens when things fail, when you have to scale to varying user loads, when you have different workloads, different effort you need to invest inside, say, the application versus the web server. And this is a very natural, very flexible structure to do that. Okay, great. So we have individual components stitched together into a graph, and these together, all together, provide and fulfill the service requests of our users. Okay, that's sort of my example one. My exhibit two would be exactly the same thing, but quite different. And this idea that you take such functionality, distribute it into individual functionality and provide that separately, that is very natural to a networking environment. And in a networking environment, you do that by looking at individual functionality that you stitch together into a graph, right? Just the functionality is different. Could be a firewall, could be a load balancer. And indeed, you might also have an application server sitting somewhere, maybe such a web server, maybe something more specific, more complicated, right? So it's not exactly the same thing. The type of load you deal with is somewhat different. Here you have requests that might be composed of multiple packets that only together make sense. You might have more transactional semantics. Down here, you probably have more streaming behavior. You want to push a stream of packets through your individual boxes, and you can look at each packet individually. You don't need to think of application level requests. But yeah, okay, fair enough. This is somewhat different. But on the other hand, there's lots of commonalities here between such end user facing types of applications, like here in these microservices, and these more system network facing type of scenarios which you have inside the network. Now, both of that, you need to think about the execution environment. Typically in microservices, you don't run, nowadays, you don't run a web server, application server on bare metal. You put a virtualization layer in between, right? Something like VMware or Kubernetes or something. And we do exactly the same thing. Here, we put a virtualization system in between. And then we arrive at the notion of network function virtualization, NFV, network function virtualization. Okay? So my claim is that, yes, there are differences, but there's also lots of commonalities. And I'd like to focus on the commonalities, not on the differences here today. So what I actually can think about is basically I have sort of an abstract service described by a user accessing a component A, which then needs to access components B and D, and maybe B needs to access C in order to fulfill the service request. And I don't really care whether this is application layer or system layer. It's a box running software, right? And my job now is, because this is great. Such an abstract service description is something that my software developer, my software engineer is going to produce. But my job as a systems person now is to think about, I need to execute that. And to execute it, I need an infrastructure. And that infrastructure might comprise data centers. It might comprise routers with some execution capability. It might comprise a base station with a little edge server stuck next to it. And they're connected by links, right? And this is this cloud edge fog buzzword triad that you find in this context. But to be honest, I don't think this is actually very useful distinction to artificially separate my network, my infrastructure into, okay, this is the cloud and this is the edge and that's the fog. And then you start fighting over terminology. And yeah, is this still fog? Is this already edge? And that's totally pointless, right? Because at the end, this is infrastructure onto which I can map software to be executed. And this mapping of my service, of my components that will execute my service onto the underlying infrastructure, that's an interesting problem. And that's the so-called management, excuse me, not talking enough these days, management and orchestration problem, abbreviated as MANO, right? And there's tons of problems in this context. Let me just give you some examples of what we need to think about here. So one example problem here is placement. Where do I put all these individual components? Maybe assuming that I know where a user exists, right? So let's say I know that my user sits here and injects requests from here. Then I might have to put A here and B and D and C here. And this decision could be driven by the fact that I don't have enough computational capacity to run everything here. This might just be a base station with a tiny little bit of computational power, or a router somewhere, it doesn't really matter. And it's also driven by considerations of maybe I can reuse that for the service executions, so it's not an isolated service for one user. Maybe it is, typically it isn't, but something I can share across. So why am I doing that? Why am I not just going full-fledged towards the cloud? Put everything in the cloud, right? Endless computational capacity, I don't need to worry, and it's probably going to be cheaper. Cloud infrastructure as euro per execution capacity, per unit of execution power, is probably going to be cheaper than such a complicated infrastructure. Well, the reason usually is latency, right? That's the driving force in many application scenarios. Let me just give you two concrete examples, maybe three examples. Could be gaming, where you want low latency to make your gamers happy. It could be autonomous driving, etc., where your users are cars that need to interact with each other, or manufacturing, where these users here are actually machines that need to coordinate with a backhaul server somewhere to do predictive maintenance. And you don't want long delays there. Or you might not have the data rate actually in some setups with your factory sitting somewhere in a developing country. Okay, so I need to answer the placement problem. Where do I run which component? And typically latency is a key consideration there. Now, what happens? What happens if an additional user comes in? Let's say it pops up here. Well, okay, fair enough. I could route the requests over here, but that doesn't look like it's going to be a good idea from a latency perspective, right? I'm carrying the traffic all the way over the internet just to have it go back partially. So obviously, I want to complement the placement problem by the scaling problem by thinking about, could I do an additional instance of this abstract component here? I'm spinning up an additional instance down here such that I can have my user request maybe mostly served from here and only occasionally have to talk to BNDs here, right? Again, latency drives my decisions in such a situation. So the latency I'm talking about here was mostly latency for user requests, right? So I want short round trip times, etc. But there's also the latency on a more operational perspective, and it's the time I have to decide such things. The time I have to do management, orchestration decisions like placement and scaling. I need to be very agile, I need to be fast for that. So a typical requirement, if you look at the 5G documents, they're vision type of documents. I want to be able to deploy such an abstract service on my concrete infrastructure within 1 minute. 1 minute as a typical ballpark number in such a situation. Okay, so that's the playing field. That's the environment in which we have worked for a couple of years now, still doing that. And it's a very rich area in which you can think about. So maybe let me ask you, it's totally impossible for me to get any feedback. I don't think any of you has a camera on. So if you have any feedback, again, please do tell me. Maybe that's a good point to take a breath here. Everybody on the same page with me? Okay.
Yeah, it's perfectly clear.
Perfectly clear. Wonderful. Thank you. I love that somebody gives me some feedback. Thank you, Daniel. So let's look at some concrete examples. For example, we started by looking at what do we know about these services? What do we know about these components in the first place? So when we looked at that, it was pretty much unclear semantics. For example, two aspects were usually not really clear in all these European Union documentations, etc. One case was you have very coarse-grained performance models, mostly driven from cloud computation models, where you say, okay, I need a medium-sized virtual machine, whatever that might mean, right? This is sort of an Amazon type B model. Okay, sure, you can deploy that, but is that efficient? Are you using your resources in an elegant way by being so coarse-grained? Don't I want more detailed information about, okay, when I have that much load, I need to provide that much computational power, memory, I/O capacity, whatever, right? And the second point, was that the semantics actually was often quite unclear. For example, are these components stateful or stateless? So do they memorize anything about the traffic that goes through? If you have a stateless component, life is easy, right? You can tear it down, you can bring it up, you can reroute traffic, nothing bad happens, everything's great. If it's stateful, well, for a very simple example, you have traffic going back and forth, right? User, component in the middle, server somewhere, and that thing is stateful, like a firewall, deep packet inspector, whatever. You want to go through exactly the same instance. It doesn't help you if you go from user to component A to server, and then on the way back, you route via a different instance, and then you have two instances here. That breaks the semantics of that. In order to do that properly, your MANO systems needs to know. It needs to know that this component is indeed stateful in that sense, and that component I can treat as stateless and can be very relaxed about that. So we looked at ways of defining that and incorporating that information then into concrete scaling, placement, MANO operations. For example, we provided a more fine-grained way of describing performance requirements, with the idea that suppose you have your component and suppose you have traffic arriving with certain arrival rates, lambda 1, lambda 2s, whatever. Then I can tell that, okay, in order to deal with traffic lambda 1 and lambda 2, and in order to meet certain performance requirements, like timing systems should not exceed so many milliseconds with such a probability. In order to do that, I need 3 times lambda 1 plus lambda 2 plus 1 CPU units and certain amounts of memory. And then what happens is I'm going to split the traffic, load balancer style, 50% here, 50% here, right? That's sort of the gist of the model there. It's actually a PetriNet-based model where we can be very specific and very detailed about statefulness. Does traffic need to be synchronized, etc., etc. Okay, so let's assume we have that. Let's assume we have such a model in place, such information in place. Then I can actually go to the placing and scaling problem. A first idea, sort of the straw man I'm going to attack in a moment. The straw man solution could be, I'm going to scale my service up so that I have enough computational capacity to deal with my user population. And then I'm going to place the scale version, right? So let's say I have a very simplistic abstract service here, user talks to A, which talks to B. And let's say I have, from a monitoring system, the information that I have 3 units of user, okay? Could be entire user population, doesn't have to be an individual person or something. 3 units of user, and then I could run that all through one component A, which would necessitate a very beefy version of that component running on a beefy server. Okay, fair enough. Or I could say, I don't have such a server to do that. So I need 2 instances of A, which I then place on 2 different machines. And then I can group my second and third user to this component, or I can group it like that, right? Or I can do blah, 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 right? You see how this goes. I can do also 2Bs or 3As and 2Bs, etc., etc. Okay, easy, almost trivial to enumerate these options. And then for each of these options, you do a virtual network embedding problem. You solve that. Okay, as you probably know, VNE is an NP-hard problem. So am I telling you to solve in a sense, exponential number of NP-hard problems? I'm not kidding. That's not what I'm telling. It makes much more sense, and it's probably a better idea to integrate the scaling and the placement into a single problem. It's going to stay NP-hard. It's not going to go away, right? But to integrate that into a single problem and take into account during placement and scaling mutual information about each other, right? If I know that I don't have enough capacity close to user U, then I already know immediately that I need to bring up additional instances. That boils down into mixed integer, linear or quadratic problems. They're usually quadratic depending on the concrete variant you look at. And then you feed that into an optimizer and you get solutions for toy examples after hours. And then you scratch your head and, okay, I have 1 minute to do that. It needs hours for a toy example, so no good, right? Just for the sake of an example, this is what such a thing looks like. So you have your typical flow constraints, deep hidden inside. You've got sort of capacitated facility location. You have multi-commodity flow problems inside there. Yeah, that's basically what I said. So I decide which components to run where, and I'm also deciding the routing between them. Right. The NP completeness is not difficult to show. Set cover reductions, for example, are a possible idea there. But of course, this is not practical. So we looked at heuristics versus the optimizer solutions. And then you do the typical thing you do in these types of papers. You look at the quality of your heuristic versus the quality of the optimizer. And usually the optimizer should be better if you give it the right parameters. It's better, but it's not dramatically better. But in return we get much better running times. Note the logarithmic scale here. So we are something like 4 orders of magnitude faster with a carefully grafted heuristic compared to what your optimizer spits out. Okay, now that's sort of the conventional approach here. Carefully handcrafted heuristic, etc., etc. Since about a year or so, we've also looked into machine learning approaches for that, deep reinforcement learning particularly. And that's the usual mixed bag of results there. Sometimes this works really, really well. Sometimes we have examples where a deep RL approach beats even a carefully grafted heuristic in all relevant metrics. And sometimes it just doesn't fly at all. Sometimes these agents are completely lost, and we're still struggling. I think, like most people, are still struggling to recognize in which situation which is actually working better, where this makes sense. So this is the machine learning applications here are still fairly early. So we have a couple papers on that. One just got a Best Student Paper Award at CNSM. That was very nice last week. So I don't really have too many results on that yet. Okay, specifically, actually, I was cheating, right? I was cheating in the previous slide. Let's say in this aspect here, I was cheating in the sense that I sort of treated this as fixed timing system, fixed behavior, or I'm assuming deterministic behavior, yeah, right? That's probably not true. Actually, I don't really will see deterministic load and performance behavior of my concrete components. Depends a bit what type of applications you look at. Network functions are reasonably deterministic most of the time. Excuse me. Reasonably deterministic most of the time. Once you go to end-user facing applications, that's typically not true. They have large variance in their execution time, so their deterministic modeling is just plain wrong. So we do need to deal with stochastic execution, stochastic service times, and then of course we get queuing, and basically what we end up with a system like that, where now abstracting away the entire network in between. I'm claiming that, or I'm treating my network as being sort of immaterial and plenty of capacity. And then I have my load arriving from my users. I have to distribute that to my different servers, which have certain service rates. There's transmission delay. So I have transmission delay here, and I have queuing and processing delay. And basically my job is I want to find a split of my traffic over my servers such that I can minimize, for example, the average latency, right? By balancing load. And again, it's almost trivial to write that down as an optimization problem. You got your typical average time in system, the 1 over 1 minus characteristic here from your typical Markov queuing models. And then you have these variants of the capacitated facility location, which turn out to be nonlinear, right? So most prior work in that context, a couple of years ago, when we looked into that, used very simplistic fixed assignment rules. We looked into that from a convex optimization point. We looked at linearizations. Actually, even the convex optimizations were relatively slow, actually too slow. Linearizations, distributed algorithms, and well, basically, I'll skip that. You know that better than I do. Let me circle back, and that might be interesting as well. Let me circle back here to the question of specifying services. Right, I had this figure earlier. Yeah, lambda 1, lambda 2, and then I need the following. How do I know that? Who knows that? Who would know that? And who would need that? Well, you could argue that the developer of such a function could know that. You develop software, you experiment with it, you measure it, you provide performance characterizations, right? And of course, the developer of that software might also be interested in knowing that. Sure, it's cute to know whether the patch you made just improved your runtime or was actually a bad idea. But also our operators, the MANO system, the operator of the telco operator or whoever operates your infrastructure on your behalf needs to know that. So to give performance promises, you need to know how much performance is required. Otherwise, you can't know how much to charge for certain rate, and etc. So a developer might have all the time in the world to do that. A MANO system doesn't have time in the world. A MANO system had this job, remember from the requirement slide, 1 minute. Within 1 minute from handing over such a function to the operational network, I need to make the decision. I need to have it operational and serve requests, right? So I can't do complicated things there. Now, on the one hand, you could argue that, okay, no problem. Let the developer provide the performance profile, this characterization here, to the operation, to the operator, and then the MANO system just trusts, right? Sure. Trust but verify, right? So what I would like to do is I would like to automatically generate these performance models or performance profiles, and then use that to guide the MANO system into deciding how much performance is needed. And the interesting thing now is, of course, this idea has been around also in the cloud computing community. But there they mostly looked, even if they looked at microservices, they mostly looked at just individual components. Turns out, if you look at these chains, in particular network function chains, this is not good enough. You get weird performance anomalies if you just look at individual components and think, okay, I've understood what happens. And then you stitch that together and try to generalize from the component model to the chain model. One example, we looked at data rate. The data rate you can push through a component if you give it a certain amount of CPU. Okay, for things like Snowd or other intrusion detection systems, that's a certain number, right? And then you pack them together, and then you would think, okay, if I do that, I get the minimum of the data rate that I can push through. If I do A, B, and C, and B is my bottleneck, and B with this performance, running in isolation with a certain amount of CPU share, it can deal with, I don't know, a megabit per second. The other can do gigabits per second. Okay, you chain that together, and then you would think, okay, I'm sure not going to get more than the minimum there. Turns out this is wrong, and it's also in hindsight not surprising it's wrong because you got interference between your individual components. But predicting these interference between your components, that's justly hard. And we have no idea how to predict that, given the individual performance models, how they actually interact with each other. So basically, we scratched our head and said, okay, forget it, it doesn't work. You need to profile the entire chain. And then you need to profile the chain under time constraints, right? You don't have really much time, so you try to steer the profiling effort, trying to figure out at what load, at how much CPU, I get what type of behavior out of that, and you have 1 minute to do that, right? And you have to solve all this NP-hot stuff. You have 1 minute to do that. So you need to carefully steer your test runs to where they are. And I do want test runs. I'm not interested in trying to do that sort of in an analytic fashion. I have serious doubt believing that this is feasible for the type of software. Okay, so you need an environment that allows you to do such test runs, and you need a steering logic to do that. Let's talk about the environment a bit. So when you talk to a networking person and say, okay, I want to do test runs, I want to emulate such a network, immediate answer you get is, yeah, sure, Mininet. Use Mininet, no problem. Fair enough, Mininet is great. If you don't want to grow too big, or if you don't want to run software. If you want to grow big, it doesn't scale. So we came up with a version of Mininet, we called it Maxinet, right? We called it Maxinet, where we can distribute Mininet emulations across a cluster. So we would take the graph, the network graph to be emulated, do min cuts, distribute this over different nodes, different machines in a cluster, and then individually run Mininet emulations there and patch the links we cut back together, so we can run that now at larger scale. Okay, and it's still just a network, right? That's not good enough. I want to do such performance profiles for a chain in a network, so I also need to be able to execute these components, these network functions. So what we needed to do, we needed to take Mininet or Maxinet and add the ability to run Docker containers. Virtual machines is by now also working. We started with Docker containers. To add Docker containers into such a Mininet environment, run arbitrary software inside over such an emulated network. And that turned out to be actually very successful. This is since in the open source MANO, ETSI's open source MANO sort of standard release model. Since release 3, this is an integrated component inside OSM. Right, so overall, what does that give us? That gives us a rapid prototyping environment as well as a performance characterization in an automated fashion of such composed services inside a realistic network environment, and we can do that even at scale, right? So overall, let's take a step back from this emulation infrastructure. Overall, this allows us to have a practical performance evaluation approach for either individual components, but also for MANO algorithms. Say you have a better heuristic, you have a better approximation-based algorithm to do scaling. Fair enough, you can do that in a simulation, or you can take this algorithm and you give us a service spec. What's the type of services you want to look at? A load specification and an infrastructure specification. Okay, infrastructure spec is usually not too difficult. You look at something like Internet Topology Zoo, that gives you an idea of what's going on, how typical networks look like. A service spec, everybody has a different opinion of what VNF or microservices actually are going to run. So since we don't want opinions, we want facts, we started collecting concrete information about, we call it SoftNet, Softwareized Network Data Zoo, where we are collecting both the source code for open source, obviously, open source network functions, as well as performance profiles, performance characteristics for that. So you can just clone that repository there if you want to play with this data. We also very much welcome contributions for all type of researchers. We hope to have here sort of repository of standard examples. I was not introduced by my dark past. I have to admit I have a dark past in my future life. I did parallel computing once upon a time. And the parallel computing guys have one big advantage. They have standard benchmarks. Right? They have their standard benchmarks. Everybody agrees they are bad, but they're still you have your lin packs, etc. And then you still know that, okay, I can use this benchmark. We are very bad as such a network softwareization community. We are very bad at agreeing on benchmarks, on standard scenarios. And we hope that this can contribute a little bit to this gap. So standard infrastructure spec, okay, that exists. Soft network data suite to give you an idea about the components. And then, yeah, you're still scratching your head and saying, okay, and what does my load look like? Where in my network does load from how many users at what rate actually arise? I admit I'm still hand waving there, right? You tell your student, okay, do a Markov modulated Poisson process, or do a inhomogeneous Poisson process driven by time of day. Go look it up, and then you look at the ceiling, right? There's not much empiric data from what we found for that. I think this is a big gap in the entire way of doing research in that area. Okay, but suppose we have come up with all that. Okay, come on. And we can take all that, stuff it into what we call an evaluation generator. And sort of we have different backends. And these backends can either do, they can generate Petri nets. Again, you take then the Petri net specification, put that into an analysis tool for Petri nets. And that, again, that just works for toy examples. That doesn't scale very nicely. Or you can generate simulation code. That's fairly straightforward. That's almost embarrassingly straightforward. You generate code for something like Omnet, and then you run your simulation. Or you can also, via a different backend, generate configuration files for ContainerNet. So you run all that code here in an emulated environment. And different backends would be not too difficult to implement if you want to have something else sitting back here. Again, this is something that might be useful if you are experimentally driven in your research. We're happy to provide code for that. Okay. I think with that, I'm done with this first part of my talk. Maybe let me ask, by the way, if there's any questions or any thoughts on that. It's terrible if the guy stops talking, right? Then you need to pick up.
Just maybe one question from not the last things you talked about, but at some point you discussed the fact that for the placement of function, including queuing, you have a modeling that mix both queuing and placement, if I understood well. But you didn't talk about heuristics about that. Did you work about heuristics also?
We also looked at heuristics for that. Yeah. We actually have a distributed version for the heuristic, which seems to make a lot of sense in this context.
And I was thinking about because it's complex. It's a complex thing to do all the things together. But sometimes you can have some modeling, some kind of profiling of what happens with queuing, and then apply the profile to the placement. I don't know if you try things like that.
Implicitly, yes. Need to go back here.
So it was, yeah, it was really at the
somewhere here. Basically, this is basically here the timing system, and we kind of replaced that by linearized versions. And in a sense, this is the modeling you're talking about, right? And once I'm here at linear or affine functions, this becomes so much easier to deal with.
Okay.
Okay, I will. Okay. Another question. I have a feeling that the introduction of slicing may simplify somehow this problem, right? It will introduce some. It will reduce the dynamicity of the story.
Mm-hmm. Yes, but at a very high price, right? Slicing means, if you look again, queuing theory 101. It means you replace a big server by many small servers, and we all know that this is the inferior solution. So slicing is a terribly bad idea. I think it's the worst idea since I don't know how long. I don't know why people get so excited about that.
Because of the problem you are highlighted, there are so many constraints, so many different objectives and somehow contradictory objectives that if you want to model all together, although theoretically, of course, because of stochastic multiplexing, you will have the best option. But when you want to really implement, it seems that it is easier to find not the best, but a good solution if you have this slicing. By the way, you don't need to allocate hard the resources to each slice. It's just most about the placing story, about having the right functionality in the right place. And then, of course, in some cases you want to allocate resources hard. In other cases, not. But it seems to me that it will simplify a little bit the problem, because if not, you have so many variables that it sounds difficult to achieve.
I fully agree. Basically, slicing is sort of chopping the big problem again into sub-problems and solving these sub-problems one after the other. But at each time you do such a split, you lose quality of the solution. And whether this is a big problem or a small problem, whether you are willing to take that hit or whether you say, no, I don't want that. I want the good solution, the better solution. Maybe it turns out that indeed with sort of pre-sliced approaches, while theoretically you lose some optimality, in practice you're still better because the more complex solution would take hours to compute or days to compute when the sliced version has already found something. Entirely possible. Yes, I totally agree. Totally agree. From my understanding, slicing is mostly a marketing tool. I don't think that has such a big justification on its own footing as a technology. But hey, I mean, marketing is important, right?
I don't think it's only marketing, because, for example, if you're talking about 5G and beyond, the fact that you can define the small cells as a service, it's a way to enable sharing resources that was not possible before among different players. It was possible. You're right that it was possible, but in the field, when you looked at the standards, it was quite complex. With this new way to do it, the new protocol, the new signaling, it seems for me that it's much easier to share resources and to share spectrum. Again, you are right, it was possible before, but at a very high price from the protocol's point of view, and no one implemented it. And today there is a trend towards this. This is the feeling I have, but I will be more than glad to have your feedback on that.
I think that's going to be a very interesting discussion for years to come.
Definitely.
Also, if I hear different things from different manufacturers. Some of them say, yes, slicing, absolutely, this is what we need. Operators seem, again, different stories. But they also hear manufacturers who say, yeah, we do it because we have to, but yeah, it makes no sense. So I don't think I think the jury is still out there. What will be the best pragmatic compromise there? And again, there's certainly a difference in what is pragmatically doable compared to what we could do on a clean slate with everything, with infinite complexity being feasible. Sure, I fully agree.
Okay.
Okay.
Thank you.
Sure. Any other questions?
An observation, maybe. Yes, from one hand, maybe slicing can simplify the problem, or it may also complicate it in case the resources are allocated dynamically, because then, at least in your problem, you have a fixed capacity that you know. But if in the upper layer there's someone who changes the available capacity for you and the available computing for you, then I guess the problem should be dynamic, adaptive, etc., etc. I don't know if you've studied this problem or.
I totally agree, and that might be one example where I'm just going to go to sort of a wireless version of that. We looked at exactly the same thing in a wireless network, in a wireless ad hoc network. Just as one little example, where we look at so-called acoustic wireless sensor networks, and that's driven from colleagues in EE who are building acoustic applications. Think like distributed microphone arrays in conference halls. That's sort of a typical application for them. And then you do have that problem that you want to have the acoustic signal processing chains, because again, latency matters, distributed as microservices inside your microphones. Basically, you got sort of Raspberry Pi type of infrastructure there. And then we started talking, and then basically this idea, okay, I'm a one-trick pony, right? I know one trick and I apply it everywhere. So basically we thought, hey, we do the same thing. We deploy these microservices, place that inside my wireless network. But now the problem is that what previously I treated as a fixed capacity, the capacity of my link was fixed, right? It's a fiber optic thing, it doesn't change. Here, it's a wireless link. And now the placement implies or leads to load being differently distributed inside my network, leads to my data streams looking different, leads to the interference situation in my network being different, which influences the capacity of my underlying infrastructure, which influences my placement, right? So I have exactly that situation. I have such a vicious circle going back and forth. And then this is just me, because I have everything under control here. If I have sort of an external player who influences that, I guess all hell breaks loose, right? Then I totally agree with the comment, and this gets really, really nasty.
Yeah, thanks.
Yeah. This is actually something where we also have some ideas how machine learning could work out. We have some first results where this actually gives decent results, but it still fights hard against a good heuristic there. Okay, maybe let me just flip through the slides very quickly. So we also look at industrial automation scenarios. You got your plant, you got your sensor and actuator controllers going over wireless links. And this is sort of my default case where I think machine learning makes a lot of sense. You have sort of a radio resource manager who needs to assign channels here to the controller, talking to sensor A, sensor B, actuator, et cetera, So which sensor actuator uses which channel? And again, I have fluctuating channel characteristics, so I have exactly the same situation again, like we talked about before. Somebody here, it's nature or the environment changes my available capacity, even without me being aware of that or being explicitly told. Maybe I have stochastic information about that. And here DRL actually soundly outperformed, really worked much better than all the natural protocol ideas that we had. Right? I admit we didn't invest too much work in coming up with standard conventional protocols there, but sort of the natural ideas, round robin, greedy versions of that, et cetera, not even all on the slides here. They all got beaten around the ear by a fairly straightforward deep reinforcement learning scheme. So that was one of the examples which I mentioned, where this really, really works very well. Okay. Well, mobile networks, so together with Huawei,
just a question,
yes,
sorry,
yes, please. Yes, please.
On the results here. So is it simulations or emulation, or
that is just simulation.
Simulation.
We still need to put that into a concrete test bed. This is still not. This is on the agenda, but it's not done yet.
Okay. Okay, thanks. Now, just because we know that in simulation we can get some results, but then in real environment it's maybe more difficult.
Yeah, it is always surprising when reality does not obey the simulation, isn't it?
Okay. Okay,
yeah.
Thanks.
Okay, so maybe a couple words on mobile networks. So we currently are looking at handover offloading decision schemes together with Huawei. That's one of these beyond 5G things. And data centers, we looked at various aspects, programmability, traffic engineering inside data centers. And again, here we're trying to see whether machine learning makes sense. And that's one example where it doesn't. So all we tried here, maybe somewhat approaching decent heuristics, but far away from. So far, we have yet to find something where we outperform a normal heuristic in that sense. Right. Okay. I think I'll stop here. Let me just briefly summarize. So I think this idea that you have a service being composed of multiple individual components which have to work together. This is here to stay. This is standard software engineering practice, and that's not going to go away, right? Running that, once we leave the comfort of the data center where everything is under control and we have ample capacity, et cetera, that's still a challenging problem. And running such composed services into an ill-defined, modified, volatile infrastructure, I think that's going to be the order of the day for some time. As we just had the discussion about, do I pre-slice or don't? How do I do that? I think that's going to keep us very busy. The application scenarios, Car2X, edge computing, etc., they are legion. And I think there is opportunity and necessity to look at the full richness of all possible methods. I know it's very fashionable today to always throw a machine learning approach at a problem and hope it sticks. But I'm not convinced that this is always the right solution. Sometimes it's great, sometimes it's just pointless, right? And here, understanding this also the difference between sort of the model-free and the model-based versions, I think that's also going to be interesting in the next couple of years. Okay, I guess with that, I'll stop. And I'm happy to take some more questions.
So thank you a lot, Holger, for your presentation. Very interesting and very quite large scope, in fact, in terms of domain that are mixed together. So any question in the audience?
Yes, hello, this is Bela from Nokia Bell Labs.
Hello.
So my question, sorry, can you hear me?
Yeah.
Yes.
Okay, so you have shown this slide with the different topologies, A, B, C, somehow distributed on the different nodes.
This one?
So yes, so in this, I mean, for me, the cloud means that you can have A plus B, A plus B plus C, etc., etc. So you can have all the combinations possible.
Maybe the cloud symbol here was a badly chosen icon. I don't mean that this is a cloud data center like a Google Big Iron data center here. This could just be your base station. This could be a base station which has attached to it a little edge cloud server, right? So I'm not saying I have infinite capacity here. It could be very small amounts of computational capacity. Make sense?
Yes, it makes sense, but actually what happens, it depends on the charge, because once again, you can have A in a first node and A plus B in the second node.
Why would I want to have A plus B in the second node? I could understand to have A and B here. Duplicating A over here, why would I do that?
I don't know, this is just to say that the cloud means topology agnostic. You don't have topology anymore because you can run each single microservices in different places. So it's not only not deterministic at all, but it's completely the opposite. Everything is flexible.
Oh yeah, with that I agree.
You may want to have A plus B in the second one just because you don't have enough capacity in the first one, the one that is nearby you. Yeah, you want to.
No, what I mean here is that a priori optimization is not enough. You understand me? So
okay. I fully agree. Actually, this is also one other model we look at. Basically, the idea that I have the software. I have all software everywhere, right? So I don't have pre-allocated, this software only runs here, right? An alternative way of thinking is to say that all my software is everywhere, but I still need to decide which flow gets treated where, in particular for the stateful stuff, right?
Yeah, this is more realistic, yes.
Yeah. I usually start talks with this model. Personally, I find it easier to imagine, but that's probably a matter of taste here.
Thank you.
I fully agree that this is also an interesting alternative model for that.
Any other questions? So maybe we can stop here. So thanks again, Holger, for your presentation and your time. And
thank you. Thanks for the
I hope
invitation.
we will
Thanks
be
for
able
attending.
to see each other during our workshop links where we invite people from the scientific committee. And hoping, and I hope that things will be better than now for that.
We
At
all
that
hope
time,
that.
yeah. Holger, thank you very, very much.
Thank you.
Thank you.
We'll be in
Bye
touch.
bye.
Thank
Bye
you.
bye.
Bye-bye.
Bye.